SwayamPrabha. Digital India. Educated India.
Welcome back. We are going to now start a new topic. It's entropy, and this is a learning objective of this particular topic. I will start with the application of second law of thermodynamics to processes. So till date, what we have learned in the second law of thermodynamics is related to thermodynamic cycle. Okay, or in general, the second law of thermodynamics was applied to cyclic process. However, our interest is to understand the application of the second law of thermodynamics to processes which we deal with our daily life, or for example in an automobile, or combustion of a certain gas, or in general cooling of a substance at room temperature, for example. So in this direction, the Clausius came up with inequality, and this is something which we are going to discuss in today's lecture, which will be called Clausius inequality, which is true for all reversible or irreversible processes. Okay, so let me just write down this. In the previous lectures, what we have gone through is your Kelvin-Planck statement or Clausius statement, which was related to thermodynamic cycle, in particular dealing with the high temperature source or low temperature sink, and the devices were operating at under cyclic conditions. But what is needed is more of quantitative information in order to come up with the explanation of a certain process to be valid or not, okay, or feasible or not feasible. So in this regard, the Clausius inequality is a quite a useful criteria, and is valid for all reversible or irreversible, okay, process, or since we are dealing with here, we will still say cycle. So this circle represents cycle. Okay. So let us try to derive this using heat engine and refrigerator. So let us consider first a reversible heat engine. Okay. So consider reversible heat engine, okay, which essentially is nothing but a Carnot heat engine. Okay. So you have heat engine which takes a certain amount of heat QH from a high temperature source and reject QL amount of heat to a low temperature sink and delivers a work which we are going to say W reversible. Okay. Now let's look at the change or total heat for this particular cyclic process, and this would be nothing but your QH minus QL for a given cycle. Okay. And considering QH is going to be more than QL, this is going to be greater than 0. Okay. Now since these are source and sink, so the temperature TH is constant and TL is constant. Let's look at this expression del Q by del T, which is going to be your QH by TH minus QL by TL. Now we know for a reversible heat engine or Carnot heat engine, based on your absolute temperature, the ratio of the Q is proportional to temperature as done by Kelvin. So which essentially means your QH by QL is nothing but TH by TL for this reversible heat engine, and thus your expression del Q by T is nothing but 0. Okay, so this is one expression for the reversible heat engine. Now if you consider a limiting case when your W reversible approaches 0, or in other words your TH approaches TL, in that case for limiting case, this will approach to 0. Okay. So thus for reversible heat engine, this expression is greater than as well as equal to, because this condition will arrive when your TH approaches TL, or in other word your work output is 0. Okay, and the other condition would be okay. So even in the limiting case, you will have this particular condition met. This is for the case of a reversible heat engine. Okay, a generalized statement. So now let us look at irreversible heat engine, which is being operated at the same conditions TH, TL. Okay, and it takes the same amount of QH. And let's now look at a reversible heat engine operating on those conditions. Okay, so this is a irreversible cycle or heat engine. Okay, between the same TH and TL. Okay, and it takes the same amount of QH. Okay, so as we know from the second law tells you that for the reversible heat engine produces the maximum amount of work. So if you're considering irreversible heat engine, essentially tells you that the work corresponding to irreversible heat engine would be less than that of a reversible heat engine, which essentially means W irreversible is less than W reversible. Okay, now you can make use of the first law, simple energy balance. You know that for a system containing corresponding to the heat engine, your QH minus QL is nothing but work. Okay, this is true for reversible or irreversible cycle. Okay, now you can substitute this expression here. So now we have an expression QH which is same for irreversible and reversible as we considered here, and QL will change for the irreversible. This should be less than QH minus QL reversible. Okay, now this will cancel out, which essentially means your heat loss during an irreversible cycle is more than that of a reversible cycle. Okay, now based on this, now you can look at specifically the expression which this expression of del Q for the cycle. Okay, now for the case of irreversible, this will be replaced by QL will be replaced by QL irreversible. Now this is more. Okay, but even though this is more than the QL reversible, the difference still will be greater than 0 considering QH is more. And what about your del Q by del T? So del Q by T is going to be your QH by T minus QL irreversible by T. Now considering for the reversible this was 0, now this is more than QL reversible, and considering here negative, this should be less than 0. Okay, so this is the expression which comes out from this analysis. Now if you have a system where the irreversibility can be increased by, let's say, due to the finite difference in temperature between the system and surrounding, for example, or frictional loss, if you have more irreversibility, this term will become more negative. Okay, for increasing irreversibility. Okay, and what about this? If you have more irreversibility, this will approach to 0 for increasing irreversibility. Okay, so in a specific limit, in the limit let's say when your W irreversibility is 0, which essentially means or it approaches 0, your del Q should be 0 and del Q by del T is less than 0. So that's what exactly what we meant by increasing irreversibility. Okay, which essentially means that the work output is also reducing and eventually it will be approaching towards 0, which essentially means these conditions are going to be the case for highly irreversible process. Okay, so this was the case when we discussed irreversible heat engine. So that means for all irreversible heat engine, the following condition would be true. Okay, Okay, so this was the analysis based on the heat engine. First we did irreversible and then we did irreversible. Let's now look at the refrigerator, particularly to complete the demonstration here for the Clausius inequality. So now consider a reversible refrigerator cycle. Okay, so which essentially means that you have a high temperature air sink, and this is R. There has to be some work. Considering reversible, this is W reversible, and some heat is extracted from a low temperature reservoir. Okay, so let's look at this terms of delta Q for this cycle. This is going to be your QL into the system, and then this is your QH minus QH, and considering QH is going to be more than QL, this because of the work supplied or work done on the system here on the refrigerator, or the work input to the refrigerator, thus QL minus QH is going to be 0. Okay, and what about delta Q by T? Okay, for the reversible, as we already discussed, this based on the Kelvin temperature scale, this for the reversible cycles, this should be equal to 0. Okay, so in the limit TH approaching TL, your del Q should be approaching 0, and your del Q by T still should remain equal to 0. Okay, so this would be the limit for the case. Okay, now let's look at, so this was for the reversible refrigerator cycle. Now let's look at for the case of irreversible, okay, refrigeration cycle. Okay, okay, and then we are considering that it receives the same, considering same QL, and the rest of the conditions such as TL and TH are same. Okay, so from the second law of thermodynamics, we know that for the refrigeration or reversible refrigeration cycle, the amount of work required is minimal in order to deliver the task. Okay, so when you have an irreversible cycle, it requires more amount of work in order to do the same operation. So in other words, we are saying that W irreversible is going to be more than W reversible for the case of refrigerator cycle. So input is more for the refrigerator cycle compared to the reversible cycles. Okay, so we know is W reversible should be more than reversible. That is, W required will be greater for irreversible refrigerator. Okay, so let's now look at first law. First law again tells you that QH minus QL is nothing but W. You apply this for reversible and reversible because it is true for both. So QH minus QL, you apply it here. Irreversible should be greater than QH reversible minus QL. Okay, so this essentially means QH irreversible is greater than QH reversible. So this essentially tells you that the heat rejected for the case of irreversible is more than that of reversible refrigerator cycle. Okay, so now let's look at this expression of the change overall heat for the cycle. This will be your QL minus QH. Now for the case of irreversible, we'll put irreversible. Okay, now irreversible, as we already mentioned here earlier, that this for the reversible refrigerator cycle, this expression is always less than 0 or equal to 0 depending on the limiting case. But now when you have irreversibility, this term is more, which essentially this is going to be further negative, and the other term del Q by T is going to be more negative. Okay, so this also tells you that if you increase the irreversibility, this will become more and more negative. So this also tells you that increasing irreversibility this becomes larger in negative value, okay, or negative direction. So let me just summarize. So this is a summary here. For all possible reversible cycle, which essentially means your delta Q can be greater than 0 or less than 0, because it can also have your refrigerator cycle or heat cycle. Your del Q by T over cycle will be 0. So this is for all possible reversible cycle, and for all possible irreversible cycle, again including the heat engine and as well as refrigerator, where you have considered different sign of delta Q, okay, your del Q by D is going to be less than 0. So thus we can now conclude that for all cycle, whether it's reversible or irreversible, your del Q by del T should be less than or equal to 0, and this is nothing but your Clausius inequality, where the equality is true for reversible cycle and inequality indicates your irreversibility, okay. So this is what would identify your processes, okay. So let's look at a specific example here and ask the question that if a certain process is being defined, whether this process violates the second law of thermodynamics. So now we can analyze such a problem using quantitative measure, okay, and that's what we are going to make use of it. We are going to try to find out what is the Clausius expression or inequality of Clausius, okay. So let's look at specifically this process. Here you have two particular device which either takes a heat or rejects, so that is going to be your boiler and condenser. So overall your del Q by del T for this cycle can be simply sum of your del Q by del T for the boiler and that for the condenser. So without going and solving numerically all aspect of it, let us me just go through a bit of how to solve this problem. So let's assume this heat corresponding to the boiler is going to be your Q. So this is nothing but your 1 to 2. If you look at your process, this is 1 and this is 2. So this is going to be the heat supplied to the boiler, okay. So this is going to Q1 2 and this is going to be your Q, let's say 3 4, heat rejected from the condenser, okay. So this is nothing but del Q. Now the temperature of the boiler and the condenser are constant. So this is T1, this is going to be 1 by T3, 3 to 4 del Q, okay. Or in other words we can write is simply Q1 2 by T1 plus Q3 4 by T3, okay. Now considering 1 kg mass basis, okay, then we can replace this or then we can write Q12 is simply, because this is saturated liquid and this is saturated vapor, it is simply the vaporization, change in the enthalpy between the vapor and the liquid, because this is a steady flow device. So in that case is we have to make use of the control volume expression. So this is nothing but going to be QS2 minus H1, okay. Similarly for Q3 4 this is going to be H4 minus H3, and the T1 would be your Tsat, okay, at the pressure which is already given to you, 0.7 megapascal, and T3 is again, if you look back here, this again is given the pressure 15 kilopascal, is Tsat at 15 kilopascal, okay. So thus you can simply plug this information and calculate your value from based on the steam table. It turns out that this for 1 kg mass of the steam, this value is minus 1.087 kilojoules per kg Kelvin, and considering is negative, this satisfies the inequality of Clausius. That means this particular process do not violate the second law of thermodynamics. So this is very valuable tool to analyze the validity of a certain process or the feasibility of a certain process, and thus it's quite useful for engineering applications. Okay, so with that I am going to end this particular lecture, and in the next lecture we are going to define the term called entropy, and we'll analyze increase in entropy principle and other aspect of the entropy. Okay, so see you in the next lecture.